Okay, I think we are recording. So, welcome to learning target number 5. Purpose of this learning target is to be able to describe thermal energy transfers in a chemical reaction in terms of bond enthalpies. And we'll define all of that stuff momentarily. So what we're going to do here is we're going to introduce this thermochemistry / energetics unit by first showing you this nice little video. And this video is of me performing the whoosh bottle demonstration that you might have seen before if you were in my honors physics and maybe last year's class. And there's a question I'm going to ask at the end. You can think about that question after the video is over.
This really has nothing to do with, well, it has somewhat to do with what we're going to talk about today, but it's to start off the energetics / thermodynamics / thermochemistry unit by doing something that catches on fire, because catching something on fire is, oh, look at Robert, he woke up, because it's exothermic. So what I have done is I've taken this bottle and I have filled it with methanol. Methanol is the smallest alcohol with 1 carbon, has a very low vapor point. So I basically set this up for you about 7:05 this morning, and I've been allowing the methanol to vaporize inside the water jug. How many people have seen this before? Not tell. All right.
Very boring.
It's boring?
It's not boring.
It's boring if I screw it up.
Yeah.
So what I'm going to do is I'm going to, oh, it's a good one because it just went poof a little bit. I'm going to pour the excess methanol down the drain a little bit. Cap it. I'll light my stick on fire. You can go, Kirsten.
She's been going.
Oh, she's been going? Yeah. Okay. 3, 2, 1.
Okay, that was really.
Oh my gosh.
Was that endothermic or exothermic?
I don't know.
All right. So hopefully you are going to be able to answer that question if it's endothermic or exothermic, but you already might know the answer. So let's take a look at what we mean by energetics. Energetics relates to the amount of energy needed to break and form bonds during a chemical reaction or a chemical process. So it doesn't have to be changing reactants to products. It could be doing other things as well. Really important concept here. Energy is inputted into a system, into reactants to break bonds. It's released from a system to form bonds. And we're going to watch another video here so you can see why that happens.
Let's talk about bonding. Let's say you have 1 atom. It could be hydrogen and another one. Why not just do 2 simple hydrogen atoms? Now, each one of these hydrogens has 1 electron existing around the nucleus. If I bring these 2 atoms close together, well then the electron from 1 atom is attracted to the proton in the other atom, and the electron in this atom is attracted to the proton in the other atom. So there's this mutual attraction between the electron over here and the proton there, and the electron here and the proton there. And you can feel that attraction with atoms. Now, of course, this isn't electrical attraction that we're feeling, but it simulates that feeling. And if you release them, they form a bond. And in forming that bond, they release energy. That you can hear in the form of sound. The same thing happens with bonds on the atomic scale. When the bond forms, energy is released, and if you want to break that bond, you have to go in there and put in work. You have to put in energy to separate these 2 atoms apart. So this is a common misconception. It's one of the main reasons I was inspired to make atoms in the first place. It was the idea that bonds store energy. They don't. I mean, I think on the macroscopic scale, if you ever want to bind things together, maybe you have to get a bunch of tape and wrap it up and put in energy to stick things together. You know, we think of things requiring energy to stay together, but on the atomic scale, it's very different. Things come together because they can achieve a lower energy configuration together than they are apart. meaning that they give off energy when they bond, and it takes energy to split them apart.
Okay, so hopefully you got out of that it takes much more energy to separate atoms into their components. And so energy is being put into the system in order to break those reactant bonds, and then energy is released when those bonds are reformed, when products are in existence. So let's talk about that in terms of why it happens. So first and foremost, atoms and molecules, you might remember, are the most stable when they have fulfilled the octet rule. That means that the majority of the elements on the periodic table want to be surrounded by 8 valence electrons, except hydrogen, who wants to be surrounded by 2 valence electrons. And then there's some octet rule breakers like xenon and phosphorus and sulfur. When we want a reaction to happen, we have to tell those atoms, hey, you're not going to have your full octet of electrons for a moment. And so we have to put energy into those molecules to get them to temporarily not have their valence electrons surrounding them. That puts them into a high energy state. It gives them anxiety. They don't want to be in that high energy state. That's why we have to force them to do it. But when a new product is formed, all of a sudden those atoms are surrounded by their 8 or 2 or odd number of valence electrons. And because they are now surrounded by the number of electrons that they want, they release a bunch of energy, like they're back to being relaxed again. And those atoms return to their lower energy state. Some reactions take more energy than others to get those bonds to break. And we'll talk more about that when we're talking about endothermic versus exothermic processes. Couple of definitions before we can do that. First and foremost, we have to define system and surroundings. A system is the reaction being observed at that moment, or a process being observed at that moment. So if I am combusting methanol, my system is my methanol and the oxygen that I'm using to catch it on fire. The surroundings are going to be what contains that reaction. So in my video, it was the water jug, it was the fume hood, it was the classroom, it was the students. Everything else that's not that system is the surrounding. The rest of the universe would be the surroundings. So when we're talking about endothermic and exothermic, please remember those two definitions. So exothermic versus endothermic processes. Starting with exothermic. If more energy is released when products are formed rather than put into a system to get bonds to break, we say that that reaction is exothermic. Energy is going to be released from the system into the surroundings. And that energy being released is in terms of thermal energy or heat. And we can measure it by taking the temperature of the surroundings. So here's a graphic. Let's say I'm heating up this chemical that's inside of this flask. So the chemical or chemicals that are inside this flask would be the system. And as that is occurring, the energy that is entering the system is going to be higher than or lower than the energy released when the reaction happens. And we say that that process is exothermic. And I would be able to tell that that is happening because if I put my hand on the flask would be warm because the flask is part of the surroundings. Let's look at this graphically. This is a energy versus time graph or course of reaction. It's how much time is going on during the course of a chemical process. When I have an exothermic process, the energy of the reactants will end up being higher than the energy of the products. That means that the reaction will tend to want to happen because it won't take as much energy to get those reactants to turn into products. This is called activation energy. And what activation energy is just how much energy I have to put into those reactants to get the reaction to proceed. So I'm adding energy and adding energy, adding energy until I get those bonds to break, and then they quickly reform to a lower energy state and I get products. What I feel as being in the outside of this system is I feel a temperature change. Temperature has gone up. Here's an endothermic process. When more energy is gained by the system, when products are formed, we say that the reaction is endothermic. That means that energy is going to leave the surroundings and enter the system. So the surroundings temperature is going to decline. So let's pretend we're melting ice. So melting ice is a great example of a chemical process. So in order to melt the ice is going to be the system. I have to take heat from the surroundings, putting it into the system, which is the ice cubes, in order to get the solid ice to turn to liquid water. So looking at this graphically, here would be my ice down here, my reactant in this case, even though this looks like A plus B for reactants. I'm putting energy into the system, into the system, into the system, into the system, until I get all of that ice to turn into water. And there's more energy in the products or in the liquid water that's formed than in the ice that I began with. And I can think about that as the molecules in water would be moving quicker than the molecules in a solid, which would be your ice cube. Reaction progress is just the time it takes for the reaction to move forward. And energy is potential energy in terms of heat. Here would be my activation energy again, how much energy I had to put in until all of those ice molecules turned to water molecules. And then there's my ending amount of energy. Let's add another definition to this. The next definition I would like to add is the definition of enthalpy. So enthalpy, which has the variable capital H, is a measure of the total thermal energy in a system, otherwise known as total heat of the system. That's why it's capital H, because H stands for heat. It is nearly impossible to know how much heat energy is in a system at a given amount of time, but it is very simple to know how much heat measurements have changed. So a lot of times we don't just talk about H for enthalpy, but we talk about change in H, or the change in thermal energy of a system. So for an exothermic process, if I have lost heat energy to the surroundings from a system, I lost heat, I lost enthalpy, my symbol for an exothermic process will be negative delta H. For an endothermic process, it's opposite. Heat's leaving the surroundings, going into the system. I'm gaining heat, so it's going to be a positive delta H. Here's another example. Don't know why I chose this picture, but I did. Found a cool picture of a bale of hay burning. That bale of hay, we'll consider that the system. The hay being on fire would be the system. The surroundings would be the farm, the city, the rest of the universe. So since the hay is on fire and the surroundings of the universe is getting warmer, so the hay is losing heat energy to the surroundings. So its symbol for enthalpy or change of enthalpy would be negative delta H. There are many different types of enthalpy out there. In the hay example, that was the change in enthalpy of combustion, because I'm taken the hay, I'm combusting it with an ample amount of oxygen to get carbon dioxide and water. So that's called enthalpy of, or change in enthalpy of combustion. I've got change in enthalpy of solution. When I dissolve any sort of salt in water, I'll get a heat change. It could be endothermic or it could be exothermic, depending on the salt. Change in enthalpy of vaporization. So going from a liquid to a gas, that's change in enthalpy of vaporization. I could reverse this and have change in enthalpy of condensation as well, and that would be going from a gas to a liquid. Heat, change in enthalpy of formation. So if I'm forming a new product, like I'm forming methanol here from its elements, we call that the change in enthalpy of formation. And both these down below here are the same. These change in enthalpies of neutralization. When I'm neutralizing an acid with a base, I will lose heat. It's an exothermic process. So we will have a value attached to that. What I would do with this page is I'd pause the video and I would take some notes and define these values. Or not define those values, but define what the symbol stands for. And that will help you later on when you're doing some calculations. Last step. We're going to start leading into how we're going to use some actual literature values to calculate whether a process is endothermic or exothermic. This is directly from your IB data booklet. This is on page, I think it's page 12, it's table number 11. And this multiplication looking table at the top here is giving you enthalpy values in kilojoules per mole of how much energy is needed to break a bond. So for example, if I've got a carbon-carbon bond, single bond, it's going to take 346 kilojoules of heat energy per mole per 6.02 times 10 to the 23rd of those bonds in order to get that carbon-carbon single bond to break. If I have a carbon-hydrogen bond, it takes slightly more energy. If I've got a bromine-bromine bond, it'll take a lot less energy. So these are all single bonds. Some of these are blank because if you have a blank spot in a data booklet, it usually means you are solving for that value somewhere on the exam itself. So they didn't put it into the tables because it will probably show up in an exam question. You got double bond and triple bond values down here, and it makes a lot of sense that it takes more energy to break double and triple bonds because there's more electrons to separate from the other atoms. So you don't need to write down this table. One of your tasks is to go to your IB nuts and bolts folder on your materials page in Schoology, or you can go down to the link below, and I would bookmark that page. It's on page 12 of that data booklet. You're going to use that for those assignments coming up. Last thing on this video is the equation to calculate the enthalpy of formation, forming products from reactants. So the change in enthalpy of formation, forming products, is going to be the sum of the enthalpies of the bonds broken minus the sum of the enthalpies of the bonds formed. If when I do this multiplication, addition and subtraction, and the value ends up positive, it is an endothermic process. If the value ends up negative, it's going to be an exothermic process. And again, these values are going to come from pages 11 through 13 on your IB data booklet. Link to the nuts and bolts folder down below. So at this point in time, I'm going to break this video into two pieces. I'm going to do the calculations on a second piece to give you time to brush up on your notes, and we will see you soon.